So, we will come back and we will continue our discussion which we had on polymers. And if you remember in the last class where we stopped, we were discussing the classifications of polymers, and we basically learned that in the first case we did separate polymers based on source, natural, synthetic and semi synthetic. Second case we classified polymers based on structures. We talked about linear, branched and cross-linked or network structures. Now, the third would be based on modes of polymerization. In true sense, we will talk about here, this is actually basically the classification based on the composition or structure, chemical structures relation between the monomer and a polymer. And in this case we have two types. One is we have addition. Now, in organic chemistry you know what is the addition reaction. Addition reaction is where two or more number of molecules combine to form one large molecule, large in the sense comparative to the other two. For example, if I have ethylene and chlorination of ethylene, just Cl2 will give CH2Cl. So, in this case it is just a addition of two reacting molecules to produce one molecule. It could be 2 in this case, it could be more than 2 also, and it happens mainly for the molecules containing double or triple bonds, where it basically adds up a new group or atoms, a molecule gets added up in forming sigma bond. So, in this case when we talk about polymers, in case of monomers, so we will talk about addition polymers in similar line. So, basically the polymers will be made from monomers just by carrying out addition reactions between monomers. For example, if I just take a butadiene molecule, (1,3-butadiene), this is the polymer of 1,3-butadiene. So, in this case is basically the addition of monomers one after one. In case of we have written n. So, n number of monomers adding up. There are other the examples which we given earlier similar to this, say like if I take a polyvinyl chloride, so from monomers we are just doing a polymerization, and this is vinyl chloride. So, this is polyvinyl chloride, or commonly it is known as PVC. Now, in this case, as you have known the definition from addition reaction, that the monomers are just get added up and nothing comes out. So, basically in this case the structure of the repeat unit is similar to the monomeric units. So, practically there is no difference except double bond is getting converted to single bond. We can have here the examples are shown as from single monomer. So, they are examples as I mentioned earlier, these are homopolymers. If we do the same thing with, for example, if we take a butadiene 1,3-butadiene plus we take another monomer styrene, then we can get addition polymer which are combination of these two, and we call that as a copolymer, okay, which is because of the space I am not writing the structure, but this is you can understand that this will be a polymer containing both repeat units from butadiene and styrene. So, it will be a butadiene styrene copolymer, and commonly this polymer is when you have about 3 of 1,3-butadiene and 1 of this styrene, we call this polymer as Buna-S, and this is done in presence of a metallic sodium. So, this Bu from butadiene, Na is from Na sodium natrium, and then As stands for styrene. So, we have a butadiene styrene copolymer, and because it is done, polymerization is done by sodium, we have a common name of Buna-S. So, we are giving examples of addition polymers. Again, addition polymer are polymers which are synthesized by addition reactions, and addition reactions you know from definition from organic chemistry is the reactions where 2 or more molecules combine to form one large molecules without giving up or giving away any other small molecule residues. The second category in this classification is condensation polymers. Now, the as earlier, in this case the polymers are synthesized by condensation reactions between the monomer molecules. And what is condensation reaction? In organic chemistry, you know, when two or more molecules are produce molecule along with production of small molecules like water or say methanol. Examples, you have a ester, say you have acetic acid plus you have say ethyl alcohol reacts and produced ethyl acetate plus H2O. So, in this case the difference between the addition reaction and condensation reaction is this. Here we are getting a additional small molecules. So, example in case of polymers would be nylon 66, which is a polyamide synthesized from, this is hexamethylene diamine plus this is adipic acid it gives So, we start with the hexamethylene diamine and adipic acid and produced this polyamide. There is a amide linkage in between in the polymer backbone. So, that is why we call this as polyamides, and the name of this polymer commonly we can write in chemical name is basically hexamethylene adipamide, but in commonly it is known as nylon 66. Now, these numbers 6 and 6 coming from all these reaction between diamine and diacids the polymer from diamines and diacids forming polyamides are known as nylon, and this number represents the number of carbon atoms in the monomers. In this case, it has 6 carbon atoms, and the acid diacid also has 6 carbon atoms. So, we call nylon 6,6. So, for example, if you have something like 5 and COH, then this can self condense among themselves and they can produce a polymer with repeating structure, repeating unit structure like this, and in this case what will you call this nylon? This is from single monomer unit amino acid, and so we call this as nylon just 6 because it has 6 carbon atoms. So, in this case if you look, there are 2 monomers producing a polymers, but look at a repeat unit. This repeat unit having 2 monomer residues, in this case we have repeat unit of from 1 monomer residues, but this is not a copolymer. Do not get confused. You can argue that because it has started from, the polymer is made from 2 different monomers, this is not a copolymer because the repeat unit, which means the polymer itself contained, polymer repeat unit contain 2 molecules individually. If you had this adipic acid only or hexamethyl diamine, they would not able to form polymers by themselves individually. So, we will not be calling this as homopolymers, but say instead of adipic acid, you have say half of it, say some other acid like CH2 in this case. Maybe I can write in the next page and giving another example. So, we talked about PET, polyethylene terephthalate, where we had this is terephthalic acid and if you take N of this and N of this, we will get okay. So, this is polyethylene terephthalate. Okay. As I wrote earlier, this is polyethylene this is ester. As you can see, we call it a polyester group of polymers, that is why the term ate is coming here, and this is a ethylene glycol. So, that ethylene unit is here in the name, and you have terephthalic acid. So, we call it as a terephthalate. So, if this is a copolymer? No, this is a homopolymer. Now, say I have the same terephthalic acid N number plus I have N by 2 ethylene glycol and plus say N by 2 butene glycol. So, now you can imagine in the polymer you will have half of the ester groups will be ethylene terephthalate and the half of the polyester group will contain butylene terephthalate. Okay. So, that is a copolymer, because here we will have one acid, but two diols. Okay. So, we will have write say polyethylene co-butylene terephthalate. Anyway, you do not have to bother too much about names, because it probably is not in your syllabus, but what you need to know, which we call as a homopolymer and which we call as a copolymer. In case of addition polymers, it was easy. You know, when you have made polymers from when we made polymers from just butadiene or vinyl chloride, you get homopolymers, and when we have made polymers from two monomers 1,3-butadiene and styrene, you get copolymer. So, that is much straightforward for addition polymers, but in case of condensation polymers, it just you have to be little careful naming which is a homopolymer and which is a copolymer. For example, even though this polymer polyethylene terephthalate is made from two different monomers, but this is a homopolymer, because you needed to make two different functionality for making ester, alcohol and acid. But within alcohol, if you had more than one alcohols, then we are making a copolymer. Similarly, you can also think about changing the acids, two different acids to make copolymer. So, this is a copolymer and this is a homopolymer. Okay. So, this is clear which is a homopolymer and which is a copolymer, and we also should be clear about what is a addition polymer and what is condensation polymer. So, addition polymer, once again addition polymers are polymers which are made by addition reactions from monomers, and condensation polymers are polymers which are made by condensation reactions from monomers. Now, on the similar line we can also distinguish or classify polymer based on mechanism of polymerization reaction. Now, when we had this say styrene, how this is polymerized? You can imagine that this double bond is where the polymerization, the addition reaction starts. So, what we need is that you need an initiator. So, I will write a general structure as something like R, and you require an initiator which could be a radical or a cation or a anion. So, one of these will attack and initiate the polymerization reaction. So, it will attack here and you get whatever depending upon what is this cation radical or anion, you get this. So, that is the initiation. And then what happened? This will further add to the second monomer. So, if I can write here plus so this will add here, or rather this will attack on this carbon and this monomer will get added to this carbon. So, like that the polymers will be formed. So, the first step where you have this, we call this as a initiation, and then these steps where this produced active compound could be radical cation or anion attacks the second monomer. So, this called propagation. Now, propagation of what? It is starting the chain, isn't it? The chain. Now, if you can think, imagine that this will further continue, and now it is second monomer has joined. Now, we will add third, fourth, fifth, sixth, seventh, eighth, and it will continue. So, in this case, the polymer is getting produced as if a chain is getting grown. Okay. The chain is forming just by adding monomers one after one. So, this type of polymerizations where the polymer are produced by addition of monomers at the end of growing chain is called chain growth polymerization, and the polymer is called chain growth polymers. So, that is the mechanism is chain growth polymerization, and the polymer produced is called chain growth polymers. So, the name itself suggests how the polymer is forming. It is forming like a chain, you know, the necklace beads like one after one. So, basically you start somewhere, you know, just you have seen the women who basically make those necklaces at home, and you can see that they add one after one those beads in the string forming the mala or necklace, whatever you call. So, that is chain growth polymerization, okay, or the polymers is chain growth. So, one more time, chain growth polymerization or the chain growth polymers are polymers where the polymers are produced by adding monomers one after one at the end of the chain. So, obviously, in this case you have initiation step, you have propagation step, and you will have termination step as well, where if I just write chain end having this, two of these chain end come and react with themselves. If I can write in different colors, so they can form, join themselves and form a different chain. There are other mechanism also where some mechanism where you can get two chains from two active chains as well, two final polymer chain. This or this can be formed. We will just take example of radical. So, if you consider that the initiator is a radical, then we will call this as radical chain polymerization. So, basically where we need initiator which is I dot, and typically it is generated thermally, which we call thermal initiators. They typically contains bonds, covalent bonds which can be homolytically cleaved, producing so those compounds which has these thermal initiators contains covalent bonds which can be homolytically cleaved into two radicals, say by heating. There could be other methods also by which you can generate radicals from this, like redox reaction or by photoirradiation, but we just for simplicity we will just keep by heating. For example, we can talk about benzoyl peroxide. Peroxides are compounds known to undergo homolytic. If we heat it, we can get two such radicals which can give 2 phi dot. So, this can initiate the chain as we showed. There are other examples like tertiary. This is benzoyl peroxide, benzoyl peroxide. There are other examples like tertiary butyl peroxide. Other examples like acetyl peroxide. There is one very commonly used radical initiators, thermal radical initiator is known as 2,2-das azobis isobutyronitril or in short we call AIBN, which has the following structure. So, these are the some example of the radical initiators, which basically if I talk about the initiator as some x, this is the initiator, and which will on heating will produce to the I dot, which will react with produced I dot, and this is the initiation step, and then it will further react with monomers and propagate and propagation, and this will finally undergo termination. In case of radical, we can actually have two types of termination. See, you have a chain where at the end we have, I am not writing rest of things here. So, there are two such can combine and produced one which we call coupling reaction, by coupling reaction, and the other could be what called disproportionation reaction, where you can get a double bond in one side and another side you can get a saturated polymer. So, this is called disproportionation. So, we know, remember we were discussing chain growth polymerization, and by taking we just combine the mechanism also. So, in chain growth, just one reminder that we were discussing chain growth polymerization, and in this chain growth polymerization the polymers are produced by adding monomers one after one at the end of the chain. So, basically chains are polymer are producing as a chains are growing, and mechanistic wise it forms, it has contains three steps: initiation and then propagation and then termination. Okay, in this second in this category is what we call step growth polymerization or step growth polymers. As the name suggests, like earlier case, in this case the polymers are produced in steps. Now, what do you mean by steps? Say in general term I am talk about say polyester formation, just say polyester formation. The examples we given earlier is the PET. In this case we have a diol and a diacid. N of this and N of this. Now, what will happen in the first? Now, in this first step this will produce a ester linkage plus a water molecule. So, if these were called monomer, when first this will form should write the other side. So, this will form this in the first step. When the first reaction happen, it has one ester bond. We call these as monomers. Remember, these are monomer, monomer 1 or monomer A, and this is another monomer, monomer 2 or monomer B. You can write monomer A, monomer B. Now, this is what is now, this contains 2 monomer. So, this is dimer. Remember, the name mer is unit, di is 2. So, this is 2 units in this case. So, we call dimer. So, now what happens? Now, the dimer will react with some monomers. So, dimer plus again monomer will give you trimer, dimer plus another dimer will produce tetramer. Again this trimer which is produced, it can react with monomer forming tetramer, it can produce dimer forming pentamer, it can react with another trimer to hexamer. Similarly, tetramer can react with dimer forming pentamer, it can react with the dimer forming hexamer, react with the trimer forming heptamer, or it can react with another tetramer forming octamer. Similarly, this goes on. So, you now will have pentamers, hexamers and so on. So, this is a statistical process. Always a small oligomer units which contains more than one, but not large number of these mers or units, they will react with each other, one carboxylic acid and group in group and hydroxyl or alcoholic in group, and this will keep on continuing. So, how this now in this case how the polymers are growing? The polymers are growing forming in steps, like they are forming in dimer, trimer, tetramer. So, it is not that all the polymers are growing and at the beginning they are forming chains, polymer chains of high molecular weight. In this case they are forming in steps, as I explained to you, dimer, trimer, tetramer, hexamer and so on. So, slowly the molecular will get build up in this case, and that is the reason we are calling this as a step growth polymerization, and the polymers which are produced are known as step growth polymers. So, all the examples like polyamides, polyesters, generally those polymers which are produced by condensation, generally the polymers which produced by condensation of two functional groups like ester and alcohol, acid and alcohol, or acid and amine forming amide groups. So, those are the typical polymers which are formed by step growth polymers, growth mechanism. So, in generally please emphasis on the term generally, not always, addition polymers are growth by a chain growth mechanism and condensation are by step growth. This is generally the case, but there are exceptions. I will give you only one exception just to convince you that this is not always the case. If I take a exception, just one example, I will give one example. There could be there are many examples. So, I will give you one example to convince you that these are generally the case, but not always. I will take a diol. I am trying the generic structures. So, this is diol, and I will have a diisocyanate, Now, they form a polymer this is urethane linkage, this is generally called polyurethane. Now, following true definition of organic chemistry reaction, this is a addition reaction, because nothing comes out, basically two molecules or more than two molecules just get added up and forming this polymer. So, it is indeed a addition polymers by definition of addition polymers, but as you can imagine that this polymer will form by growing the chain in steps, just like we explained earlier, dimer, trimer, tetramer, hexamer and so on. So, this is an example where this is a addition polymer, but the formation is step growth mechanism. So, this is just an example to convince you that this is not always true, but in most cases, in general cases this is true, but there are exceptions, and I just gave you one example of exception. So, we classify this based on the polymerization mechanism. We classify into two types of polymerization. One is chain growth polymers or chain growth polymerization, and second one is step growth polymers, which are produced by chain growth polymerization mechanism. We will come to the final types of classification, which is fifth, which basically classification based on mechanical behavior of the polymers. Now, some books or some of your texts have classified these as based on intermolecular forces, which is not correct in true sense, because this classification is not only depend on the intermolecular forces alone, but some other factor as well. So, it is better that we classify this as the mechanical behavior of the polymer molecules to stress. and to know that we just need to know few definitions. Stress is basically force by area. So, if I take this and apply a force from, say, like if I just apply a force from this side, and then the force given per unit area is called stress. Strain is the change in dimension divided by the original length. So, if I talk about longitudinal, just in one dimension length, so it will be change in length by the original length, and this will be force by area. Now, if we plot strain in x axis and stress as y axis, and for just for simple reaction we just apply elongation stress, that means we are applying force in one dimension lengthwise. Then we can have three different general behavior of polymers. One, that with a small stress we can elongate the polymer chains, probably in later part it will have require more stress to elongate same strain. So, remember we are doing a longitudinal experiment or a tensile experiment, where basically this is a sample and you are applying stress from one side. So, basically you are longitudinally you can both sides, you are basically pulling the or applying the stress from both sides in one dimension, longitudinal dimension. So, this is your sample and you are applying force from both sides in one dimension, okay. And the change in dimension in this case del L by L would be your strain, and the force divided by the area will be your stress. So, what does it mean? It basically means in this sample the polymer material that it require a small amount of force or stress to elongate, we are talking about elongation here, to elongate the polymer or the polymer material. And in this case this is reversible. So, basically if we leave at any stage, it will come back to its original dimension. If we remove the or relieve the stress at any point in this curve, it will come back to the original state, okay. And this type of materials are called elastomers. So, elastomers where the polymers can be stretched or elongated, so more than 500%. So, basically more than 5 times, 5 to 10 times, as large as 5 to 10 times reversibly. So, high elongation maybe 5 to 10 times, or we can write 500 to 1000%. And so we call this and also reversible in the sense that at any point if we leave this, it will come back to the original state, and the ratio of stress by strain at the initial part here is called modulus, which is basically quantifies the resistance to deformations. So, in this case you can imagine the modulus is very low or very low. So, that is we call elastomers, where you have high elongation, reversible, and modulus is low, or the resistance to deformation is low. There is another extreme case, maybe I should have put it little narrower in this wide direction, which are called fibers, exactly is opposite to what elastomers. So, you require high modulus. So, high modulus, that means resistance to deformation is very high, you require much higher stress to elongate these polymers. High tensile strength, is this is the highest. What is the highest stress is can resist before. So, this stress value of this stress is the value where which can resist before it can rupture. So, that is called tensile stress. So, in this case tensile strength would be very high, whether in this case it not that high, and the elongation is low. So, it is basically exactly the opposite of those two, fibers and elastomers. So, we will have another we will call plastics, which maybe I will take up in next class, which will have intermediate behavior. So, we have not finished the we almost finished the classification of polymers based on mechanical behavior. We have dealt with, we now know fibers and elastomers, and the polymers which will have in between the behavior, they are actually plastics. And so, basically we might quantify with some numbers in the next class, but as you can understand the plastics will be somewhere intermediate. Okay. So, fibers are rigid materials which are threads, which can use for in textiles and making clothes, and elastomers are rubbers which are solids, but it can be easily deformed. So, what I will do, I will stop here today, and in the next class I will start from just complete the remaining, or just continue this mechanical, the classification based on mechanical behavior for another few minutes, and then I will be done with the classification of polymers, and I will try to frame some questions and answer for your clarification before I move to examples of some common polymers and their properties and their applications, and probably a brief description how they are prepared. So, with this I stop in this second lecture, and in the next class I will continue. As I said, I will continue little bit about this classification before I start the new topic. Okay. Thank you.